Hey everyone, what's going on? So, as you saw in my most recent post, summary sheets are now, they're sort of en masse being made, right? So I have a backlog of summary sheets that are going to be slowly uploaded from here on out. And a lot of the stuff I'll be talking about in my videos are coming directly from those, so you can follow those notes. They're color-coded, there's illustrations, all that great stuff to help you really understand general relativity much better, much easier. These summary sheets are also going to be coming out, as you've seen, on neuroscience, and I'm going to be starting these summary sheets on biophysics and many other topics as well. So if you like the summary sheets, if you like having summary sheets for your classes, for your general knowledge, that is definitely going to be something you're going to be interested in. They're going to be posted on my Patreon page until I can sell things on YouTube, and I'm getting pretty close to that point to being able to be eligible to sell things on YouTube. Anyways, today we're going to be going over the connection in general relativity, and we are going to be talking about how it's important and everything you really need to know about it in this one video. Okay? A lot of videos out there have the connection part 1, part 2, part 3, and so on. I really want to put the necessary stuff in this one video so that we can move on to talk about some more interesting things. So without further ado, let's get straight into the content. So we are talking today about everything you need to know about the connection. First, we're going to go over a little bit on the covariant derivative, and we're going to go back into the covariant derivative later after this video. But that's sort of going to help us understand sort of mathematically and physically why these coefficients are relevant. Okay. So previously, just as a refresher, we talked about transformations of mathematical objects. We talked about the transformation of vectors and covectors, and the vectors, again, the mathematical symbol we wrote down in these ways with a superscript and a subscript for the covectors. And then we had these arbitrary tensors. We have these arbitrary tensors that I define here as well. And we can keep on going down the list, right? We can have 3, 2 tensors and 4, 7 tensors and so forth. These are just examples that I have in this table. So, for example, 0, 2 tensor is 2 subscripts, 2 0 tensors, 2 superscripts. 1, 2 tensor is 1 superscript, 2 subscripts, and so forth. And then their transformation rules are here, listed right here. Right? So if I want a transformation of a vector, right, I'm going to be using, this is a contravariant transformation with respect to this, right? So and this is the covariant transformation rule. And then for our tensors, we have all these rules. Okay. One thing we want to keep in mind also is scalars. Just a scalar transforms, right, as just, it doesn't really transform. There's no matrix involved in the transformation of a scalar because it stays a number at one number at every point in space and time. Okay, that's one really quick thing to note. Okay, so now we want to understand the derivatives of these objects. So how do we do that? So, to start off, we're going to talk about the derivative of a vector. Okay, and the way we're going to do that is, here's our derivative. Okay, and we really just use the product rule. Okay, so we take the derivative of the components and then take the derivative of the basis. Now, usually the basis doesn't change. If you're talking about flat space, Minkowski metric sort of thing, this basis is not going to change. Okay, and so what we really get, if this doesn't change, this is 0, and the derivative really just turns out to be this. However, on a curved manifold, they could change, right? So what does that mean, right? That means, suppose we have some curved manifold, and here's our manifold, and here our basis vector looks like this, and perhaps here our basis vector shrinks. Okay, and that's one of the definitions we're going to use to imply curvature, right? So over here, the unit of 1 is, say, the length of this pen, and then move it over a little bit, say the length of unit 1 then shrinks. So you're going to get this shrinking effect, and if you have it in multiple dimensions, then you get curvature. Okay, and so this is what one of the definitions we're going to use to define curvature. It's sort of a loose definition because we're going to get into the Riemann tensor and all that, which is going to give us more of a concrete idea on what curvature is going to look like. But these guys are going to show up. This is going to show up in the definition of the Riemann tensor. So embedded within the idea of curvature is going to be these guys, the change in basis vectors over some manifold. Okay, so we're going to define them with this symbol mu b for right now. There's going to be a superscript, but we're going to put that in later, and we'll see how the logic in putting that superscript in. So this thing has 2 subscripts, but we want just 1. So we're going to have to sum over a dummy variable, and when we do that, we add this dummy variable so that we have a basis over here of e mu. We have a basis over here, okay? And if we want both to be e mu, well, we notice these are just being summed over these mu's, and these gammas are just being summed over. So we can switch those. So we have e mu and e mu, and what we get now is this. And this is a covariant derivative, right? So in this video I introduced this video, I was talking about the connection. This is the connection, okay? But it's sort of within the context of deriving the covariant derivative, okay? But from here on out, we're now just going to talk about the connection, okay? The reason I put this in here is, again, because the connection gives us a sense of how basis vectors change over some manifold, okay? And how these basis vectors change is going to tell us something about the curvature of these manifolds, and ultimately it comes down to these connection coefficients, okay? So how does this covariant derivative transform? So I lied a little bit. We're going to talk a little bit about the transformation of this covariant derivative before we talk about the affine connection, just to put this in a little bit more of a deeper context. So we have right here our covariant derivative. If we call this is really just a vector, right? This here is the covariant, is the component v beta, okay? What we can say here is that therefore the derivative of some vector is a vector, okay? If we multiply both sides, you can sort of think of this as multiplying. This is really a tensor product. But if we do if we multiply both sides by this basis vector, right, we get this here turns into a Kronecker delta, and which means that if this is Kronecker delta, this guy's going to go to this delta symbol, okay? And these are just numbers, right? This here is just really just a set of numbers. So this means, so we wanted delta to go to beta because of this right here, okay? Well, this means that this guy here, this covariant derivative of this vector, must be a 1-1 tensor because it brought us to this number. So when we take the covariant derivative of some vector, we actually get a 1-1 tensor. So this actually increases the rank, the covariant part of the rank of a tensor, right? We went from a vector, this object here took us from a vector to a 1-1 tensor, okay? Similarly, if you stretch your mind all the way back to calculus, there's a sort of an analogous thing that happens when you take the derivative of a polynomial. You change the degree, right? So here we're changing the rank, here we're changing the degree. And so there's something to be said, at least for what the covariant does mathematically. It changes an object to it's fundamentally a different type of object. Okay, and that's going to be important when we start talking about the connection, because the connection is going, if we want the connection to transform in some way, or what we're actually going to find is that the connection is not going to transform by means of a tensor transformation. Okay, and that ultimately comes back to defining this guy, right? This thing up here is not a tensor, okay? This right here transforms as a tensor, okay? But standing alone, this connection is not a tensor. But when we apply it in this way, when we multiply it by what looks like to be components of a vector and basis vectors, then this thing will transform as a tensor. Okay, now we're going to get into that, right? So let's talk about these guys now. So these are the connection coefficients. And at this point, I want to emphasize that a lot of this work is on the notes that are coming out. And again, you can find them on Patreon. And these notes are going to help you in really organizing your thoughts. So all the work I do here is going to be on the notes. There's going to be a little bit extra on the notes as well. So let's go straight into this. We want to consider, my apologies for the dog barking, if you can hear that, but we want to consider now this object here, right? So the blue guy here is, it's really a vector at some point x, at some point x plus delta x, right? So we can imagine our manifold. Suppose this is our manifold, and we have some vector space. Okay, and our vector in our vector space looks like this. Now if we move delta x this way, suppose this is delta x. Well, suppose now our vector looks like this. Okay? Well, we can approximate this guy here, that's this guy, with a Taylor expansion. So this is a Taylor expansion of this guy right here. This here is comparing this guy to this guy, right? So let's break this apart. This here is this guy, okay? This here is going to be this guy transposed over here, right? So suppose this is point P, and this is point Q on the manifold, okay? And this guy here quite literally is this guy, right? And but this guy here, since it's not in P, it's in Q. Since this guy here is not in P, it's in Q. Then what that means is that we can actually we can't compare this guy to this guy. But if we say that this guy is can be transposed to P, and when we do that, it looks like, suppose it looks like this, okay? We can give that a name, and that name is this guy right here, okay? And then so the difference between these two guys is going to be this, and this here is going to tell us everything about parallelism, because if these two guys are the same, that means this difference is 0. So we can actually add these two equations together now. Everything's at point P, okay? And when we do that, right, so we move some things, right, because we move the minus sign. So we're just moving some things around. We add the two equations together. We divide by this change. This is right here. This side looks like a derivative, and we'll call that's the covariant derivative, okay? And then we have all this, right? So this guy here and this guy here, right? So this is going to cancel out with this guy, but then we have this term over here as well. This term over here contains everything we need to know about the about parallelism on the manifold. Okay, so if we define it in this way, then we can get this. Okay. Okay, so this is quite interesting. So all that parallelism, if this is that parallel vector, is contained in all of this information here, right? So the idea being that this is just a bunch of coefficients. To make it a vector, we then apply this guy right here. This is that vector, and then multiply by the change, right? We're multiplying both sides by that small change. Okay, so we get this guy right here. So the connection coefficients the connection coefficients tell us something about this degree of parallelism, okay? And so what this means is, I'll come back up here really quick. So we want to keep this in mind, right? So I'm actually going to move on to a separate topic here. That's why I paused for a second. So we want to keep this in mind. So you can write this down. I'll come back to it. And this is also in the notes. But let's keep that in the back of our mind as we go through the rest of this. All right. So let's take. So now what we're doing is we're taking a vector x alpha. We always want to remember this guy as x alpha e alpha. So this is some vector on a manifold. We want to take it to double derivative. Okay. So when we take the double derivative, we find we get, with respect to tau. Okay, this is just some parameter, some arbitrary parameter. For right now, when we're considering physics, it's going to be revealed to us that this is proper time, right? And we'll see why later. But the idea here again is that when we take the double derivative of some vector traveling along a manifold, we can split it up like this, and then we can take a look at it by splitting it up more like this. This is just the product rule, right, from calculus. All right, so we apply this guy, right? Do more product rules. So this is going to be, this guy, so it's the derivative of this times this, and then the derivative of this times this, which is all right here. Okay. To get from here to here, we use this rule right here, right? Where you can almost think about these two guys as canceling. And then we get to this point right here. Now this is what we're going to define as the connection. You might think, well, this doesn't have anything to do with this right here. We'll see how it does have something to do with this right here in a bit. But the idea again is, okay, if we're going to define this as the connection, so now we have this. If we could set this to 0, if we say that the second derivative is equal to 0, well, this is the Einstein equivalence principle. This is the idea that in your reference frame, the downward acceleration of, say, when you're in an elevator, again, my apologies for the dogs, that's equal to 0. The idea here again being that in an inertial reference frame, the acceleration is 0. Okay. And I think I'll go over the Einstein equivalence principle in more detail later. I really want to just get the equations regarding the connection to you, and then I'll go into this equivalence principle in more depth later. But the idea here is that this is equal to 0, okay? We could set this equal to 0. This is the Einstein equivalence principle. That means all of this equals 0. So, and this is the geodesic equation, right? So this right here is the geodesic equation. So what we have is that the connection is somehow related to the double derivative of some vector on a manifold. It's also somehow related to some notion of parallelism on a manifold. So we want to start thinking, okay, acceleration parallelism. Is there some interesting link between the two, right? So in one case, this is physics. We're talking physics. The other case, this is really mathematics. Mathematics. I'll just put math for right now. And this is quite a deep revelation to come to, right? So these guys are vectors, some vector, but it's not obvious that it is quite obvious now that these guys are vectors, but it's not obvious that these two guys are somehow the same to one another. This notion of parallelism and acceleration, it's not quite obvious that that's quite the case. However, I do want to go into a video that sort of talks about that and sort of fleshes out some more detail on this interesting link between what acceleration is and how it relates to parallelism on a manifold. Okay, so, and then this was a covariant derivative that we came to over here. Okay, and I just added that just to be more complete. Okay, but these are the sort of the three big equations that we've come across now on this journey of general relativity. Okay, now I want to show that this guy is not a vector, or does not transform as a tensor, right? So the way we do that is we say, well, we found that the definition of this guy was equal to this. Okay, so you see now that I'm using, I've typed a lot of stuff out now. This is coming, again, all from the notes, okay? The notes have a little bit more details in them, but this, if you want this with illustrations and all that kind of stuff, again, you can just go to the notes. That will be, and they'll be coming out. If you have a subscription to the Patreon page, they'll be coming out for free of charge for you, with the minor subscription fee that Patreon requires me to have. But anyways, so we found this. So the way we found that, again, that was up, where was that? That was, we saw that right here, right here. We defined it up there. So we'll bring that definition back down here. We can flesh this out now, right? So this guy right here is right here. So we're going to take this derivative, which is this second term. All of this stays. Okay. And when we do that, right, so things get a little bit messy here, because so this term is right here. Okay. And then we want to take the derivative of this term. So we have product rule going on. Okay. here, so that this sigma is right here, and then this guy is right here, right? So you can kind of see how this works. So we have some product rule going on, and we have some chain rule going on too. And then I'll erase just to make things a little clearer. So the derivative of this was all of this. The derivative of these guys, well, that's going to be right here. Okay. And then the rest is this guy is right here. So you can kind of see how this all works out. Okay, but so now we have this big, long, ugly thing right here. Okay, so we're going to take that up here, and we're going to just look at the first term. So the first term is this guy. We're just going to move things around, right? Everything's being multiplied by each other, so we can move this guy around and this guy around to get this. The reason we do that is now because, well, this right here, that's just a connection coefficient, okay? And then all of this, well, that's just all this, okay? Copied and pasted. All right, so that's the first term. So the first term looks like this. All right, the second term, again, that's all of this right in here. So it's this also with this, right? So the second term, that's all right here. And what we can do now is what we see here, right here. We can cancel those two guys out, so we get this Kronecker delta, okay? And then we have this term right here, okay? So we have this term and this term. We can now add them together. So putting the first and second term together, we get this guy. Now this guy is interesting, right? This is the tensor transformation for any arbitrary tensor. But then we have this added on thing. Okay, this added on thing makes things a little bit complicated, right? It says that this guy doesn't transform as a tensor. This guy transforms in its own unique way, okay, with this added thing at the end, this green part, okay? So that's proof in the pudding that this connection is not a tensor, okay? But when it's, again, applied in this way, right, we do get, it is a vector because it has to be added to this so that we can get our covariant derivative. Okay? Now, last but not least, we want to write another definition for the connection. Again, I'm doing this all in one video to keep this relatively self-contained. We want to take the derivative now. This might seem a little bit arbitrary, but we want to take the derivative now of our metric. Okay, if we take the derivative of our metric, we get this. Again, this seems a little bit low quality. Everything's high quality on the notes. If you want the notes. So we have this guy. We can take the derivative with respect to the metric like this as well, because if we recall, the metric was the dot product. It served as the connection coefficient, or it served as the coefficients for the metric in our vector space on the manifold. So we can do this. To get from here to here, we do a little bit of a wild assumption. We call this metric compatibility. And what that means essentially is that when we're on the manifold, 2 points on the manifold, if we have two inner products, the inner product actually stays the same, okay? That's what that's what metric compatibility tells us, right? That we can actually move. We can actually take the derivative of this metric, right? And to get this, so that this again, if you think about this, it means that in order for this to be metric compatible, that the metric stays the same. Not necessarily. I take that back, and not necessarily that it stays the same. We're just right now actually forget this. We're just going to call this the metric compatibility case, right? Because essentially what we're doing here is that we're moving basis vectors over, okay? We're moving EJ, or EI, right, over here. And what enables us to do that is we're going to say, well, this is what we mean by metric compatible, okay? And so to get from here to here, right, we remember that this was a definition for a connection coefficient, okay? And so we get this, and then we get to this point here. We can just move the parentheses so that we have two inner products, and that ultimately tells us that this guy here is a metric. This is a metric. This is a metric. So now we have this, right? So this is what we just derived. We could take the pattern now of the subscripts and the superscripts, and we can create these two guys. Okay, just looking at the pattern of so we have I and J. Here's an I, so we need to have an I here. Similarly, K, we have a K here. J, we have a J there, and we can do that for all these other subscripts. And what we get are all of these three equations. You might know where we're going with this, right? The idea here is that we now want to add these guys up, okay? We're going to add these two and subtract this one. So when we do that, let's do that. So we're adding them and subtracting this one. That means we're adding all these guys up. Green guys are going to cancel, the blue guys are going to cancel, we're left with two of the red guys. Okay? And one of the things we're actually assuming also is that these two guys, when they're flipped, are the same, right? So R, L, J, K, and R, L, K, J. This is torsion. This is torsion-free, the torsion-free property. So we have metric compatibility over here, and we have torsion freeness over here. Okay? And what we get ultimately is that we'll get two of these guys, right? We can divide by 1/2. If we multiply both sides also by this GIM, we can do that. And when we multiply both sides by the GIM, we get a Kronecker delta over here. Okay? Kronecker delta forces us to change our subscripts and our superscripts. Okay, and what we ultimately get is this guy circled in red. So this is the metric compatible torsion-free connection. Or more succinctly, what we call it is the affine connection. And that is that's really everything to know about this connection, right? So we have this definition, we have this transformation, we have these equations, and we have. That's pretty much it. That's what we have so far. So what you can do is you can go into the notes again. They're coming out week by week, and I have summaries of all these equations on one page, one page that you can always refer to. And more summary sheets are going to be coming out for this as well. But if this is the kind of stuff that you're interested in, please make sure to hit that like and subscribe button. You can go onto my Patreon page where the summary sheets are going to be added quite regularly. And with that being said, I hope you have a great rest of your day, and I'll see you guys in the next video. Bye.